Earth, the blue marble. Water covers more than 70% of the world's surface, and yet it's the most important natural resource for life on Earth. Most of this total is in the oceans, locked in ice caps or in the ground, and just a very small fraction is available for human and animal consumption and crop irrigation. According to UNESCO, the world population may reach 10 billion people by 2050, and this led water security to be included in the Sustainable Goals for 2030. Today, most of the data used by decision makers is collected in the field. Water discharge, samples collection, laboratorial analysis, all these measures are costly and punctual, difficult to be generalized for a larger coverage. Environmental Earth observation date back more than 50 years, but for a long time, it's been limited to oceans and large areas due to satellite limitations. But recent advances improved the spatial resolution as well as spectral and temporal coverage. As the Sentinel-2 mission, launched in 2015, that provides free image from the entire globe every 5 days with a resolution of up to 10 meters. These advances are essential for inland waters, but despite the increasing number of publications, studies are usually constrained on very localized scales. Additionally, it lacks operational tools to make the models available and robust for larger areas. And that's exactly where my thesis comes in. So the first challenge is to detect water pixels in images from different locations with different water types, land cover, and atmospheric conditions. The electromagnetic energy emitted by the sun is reflected by each object on Earth, and the response is received by the satellite sensor. Different objects will have different spectral signatures, but many factors can affect this. Even water can have different signatures depending on its constituents, presence of sunglint, and others. To identify water in the scene, the pixels are grouped in multidimensional clusters using machine learning. Then, the water cluster is identified to create the final water mask. The area chosen for the first case study is in the Brazilian Paraná Basin that suffered a major drought last year. A region with more than 300,000 square kilometers has been defined, and the study period defined from 2018 to December 21. In the total, more than 12,000 images from 36 different Sentinel-2 tiles were selected for the current study. To do all this processing super fast, two geospatial clouds have been used in parallel. The Microsoft Planetary Computer, from where we download the necessary bands on demand, and the Google Earth Engine, responsible for providing the clouds and projecting the shadows on the ground. At the end, several processes are launched in parallel so that each mask covering 10,000 square kilometers is delivered in less than 1 minute. Then, all this data is organized in data cubes, mosaiced, interpolated to fill any gaps, and is being used to assess the drought of 2021 in a resolution that has never done before. But one point is still missing: the water quality. It's generally accepted that no mathematical model can be generalized for all water types and conditions across the globe, so each region has its own calibration, making it difficult for a larger scale study. To address this issue, 1,000 spectral field measurements paired with sediment concentration and other water quality parameters were organized into a comprehensive database. Then, a clustering process is performed to separate these spectra in groups in order to minimize the model error. And that makes possible to create accurate maps to assess water quality in time and space, representing a step forward towards the water security for all.